Hello and welcome to the second lecture on permutations and combinations. In the previous lecture, we looked at the concept of n factorial, which is the number of ways of arranging n distinct objects. And when we usually say arranging objects, we mean arranging in a row, as opposed to arranging objects in a circle and so on, which we will cover in our later lectures. So the definition of n factorial again was n times n minus 1 and so on till 1. For any natural number n, you can compute n factorial in this fashion. So a generalization of the concept of factorial is what is called permutations. So NPR is the number of ways of selecting R objects from n distinct objects and arranging them. So from the fundamental principle of counting, which we saw in our previous lecture, this is, so we have R positions and we have n distinct objects to fill in the R positions, and you have to do it without replacement. And so the number of ways is n times n minus 1 and so on till n minus r plus 1. This is the total number of ways in which you can select R objects from n distinct objects and arrange them. And this is nothing but n factorial divided by n minus r factorial. So this is the concept of NPR, which is a generalization of n factorial. You can clearly see that NPN, which is the number of ways of selecting n objects from n distinct objects and arranging them, which is nothing but the number of ways of arranging n distinct objects, turns out to be n factorial. And this is the reason why NPR is a generalization of the concept of factorial, where you have the option of selecting a subset of the objects and then arranging them. So we can, so far we have looked at distinct objects and the number of ways of arranging them. But what if we don't have distinct objects? What if some of the objects are identical to each other? So let's consider a more general case, where suppose we have n objects with n1 of those objects being of type 1, and these n1 objects are identical to each other, n2 objects of type 2, where these n2 objects are identical to each other, and so on. Suppose we have np objects of type p. So how many ways are there of arranging these n objects? And it is assumed that n is nothing but the sum of all these objects. So n is composed of these n1, n2, and np objects. So that's what we've stated here. And so the number of ways of arranging these n objects is nothing but n factorial divided by n1 factorial times n2 factorial times so on till np factorial. And the shorthand for this is n factorial divided by product of nj factorial j equal to 1 to p. So the reason why we're dividing by n1 factorial, n2 factorial, and so on is the realization that some of these arrangements lead to the same effective arrangement because of the fact that these n1 objects are identical to each other, these n2 objects are identical to each other, and so on. So we shall consider an example of this shortly. So let's first look at a simpler example. So consider all permutations of the word equations. So consider all word permutations of this word. So this word has 9 different letters, and notice that all of the letters are distinct. No letter appears twice in this word equations. And so suppose you were to construct all possible 9 letter words which can be obtained by permuting the letters in this word equations. So once you consider all of those words, the question is, how many distinct combinations of starting 3 letters do we have in such permutations? So any permutation of the word equations has the letters in equations filling these 9 spots. And the question is, if you consider all such permutations of the word equations and you look at the first 3 spots in such permutations, how many different combinations do you obtain in the set of all permutations of the word equations? So notice that this is nothing but considering the number of different 3-letter combinations which can be obtained, number of distinct 3-letter combinations which can be obtained from the word equations. So this is effectively nothing but choose 3 letters from these letters in equations without repetition. So we don't choose the same letter twice if it doesn't occur twice in equations, which it doesn't, and arrange them. So from the definition for NPR, it's not hard to see that this is nothing but 9p3, where we choose 3 letters from 9 letters and arrange them. And so the number of distinct combinations of starting 3 letters is nothing but 9p3. So let's look at a second example, the one where we have identical, where some of the objects are identical to each other. Question is, how many 9-letter words can be formed using all of the letters in the word Allahabad. So the first thing to do when you face with such a problem is to tabulate the letter count in the word which you're given. So there are 4 A's, 2 L's, 1 H, 1 B, and 1 D. So if you're looking at the number of ways of arranging these 9 different letters, where 4 of them are identical to each other, 2 of them are identical to each other, and so on. So we just use this result which we derived earlier, where we are looking at the number of ways of arranging these 9 different objects such that some of them are identical to each other. And so from the previously stated result, the number of ways is nothing but 9 factorial, the total of 9 different letters to be arranged. You divide by 4 factorial times 2 factorial times 1 factorial times 1 factorial times 1 factorial. Since H, B, and D occur only once, they are only one object of this type. And so you just divide by 1 factorial for those cases. And so this gives you the number of 9-letter words that can be formed, the number of distinct 9-letter words that can be formed using all of the letters in Allahabad. So once again, the reason why we are dividing by 4 factorial is because any permutation of the 4 A's, any word which can be formed by swapping the 4 A's within themselves is not going to result in a different word. It's going to result in an identical word, and so we don't want to count such words multiple times. So let's look at a third example. This example states that there are 9 candidates who are writing 2 exams, 2 different exams, exam 1 and exam 2, and the 3 candidates who are writing exam 1, and there are 6 candidates who are writing exam 2. And you want to arrange the candidates in a row. So you want to arrange the candidates in a row such that no 2 candidates writing exam 1 sit next to each other. So the question asks you to compute the number of ways in which you can do this, number of ways in which you can arrange the 9 candidates so that no 2 candidates writing exam 1 sit next to each other. Note that there are 3 candidates who are writing exam 1 and 6 candidates who are writing exam 2. So once again, you have 9 different spots to fill in a row, and you have to fill the 9 candidates in these 9 different spots. And you can't have, so in each spot you can fill in either 1 or 2 depending on whether the candidate is writing exam 1 or exam 2. And so you can't have an arrangement where this candidate is writing exam 1 and this candidate is writing exam 1. So that is not possible. So you can't arrange them in that fashion. So one of the easiest ways to arrange to approach this problem is to first fill in. So since you have 6 candidates who are writing exam 2, you just fill in the first. You first fill in the candidates who are writing exam 2 in these 9 positions, and so yeah. Even before doing that, we could. Yeah, you can't just fill in the 6 candidates in these 9 positions directly because you have to keep track of the places you're not filling in. So instead, we could first fill in we could first arrange the 6 candidates who are writing exam 2 within themselves. So let's do that here. So we first fill in the 6 candidates who are writing exam 2, and that can be done in 6 factorial ways. Since each candidate is distinct from the other, and we want to arrange the 6 candidates in a row, the number of ways is just 6 factorial. So now you can place candidates who are writing exam 1 between the candidates who are writing exam 2. So suppose you place 2 candidates who are writing exam 1 between 2 candidates who are writing exam 2. So you can see that this is clearly not allowed, because then these 2 candidates who are writing exam 1 would be sitting next to each other. So since we want to avoid placing the candidates who are writing exam 1 next to each other, what we would do is we only allow at most 1 candidate who's writing exam 1 to sit between 2 candidates who are writing exam 2. There's one possible spot here for a candidate who's writing exam 1, one possible spot here, and so on. So there are a total of 7 different spots where you can seat candidates who are writing exam 1 in between the candidates who are writing exam 2 or at the end. There are 7 spots for you to fill in candidates who are writing exam 1, and there are 3 available candidates. So the number of ways of doing this is 7p3, because you first choose 3 spots and then you permute the candidates who are writing exam 1 in those spots. So total number of ways then turns out to be 6 factorial times 7p3 by the fundamental principle of counting, since these 2 arrangements are mutually independent of each other. And so this gives you the total number of ways in which you can arrange these candidates so that no 2 candidates who are writing exam 1 are sitting next to each other. So a related question could be, how many ways can you arrange the candidates in a row such that no 2 candidates who are writing exam 2 sit next to each other? And it shouldn't take you long to figure out that the number of ways is 0, because there are more candidates who are writing exam. There are many more candidates who are writing exam 2 compared to candidates who are writing exam 1. So if there are more than 4 candidates who are writing exam 2, and there is only 3 candidates who are writing exam 1, and you cannot arrange these candidates in a row so that no 2 candidates who are writing exam 2 sit next to each other. So it's only possible in this case to arrange the candidates so that no 2 candidates who are writing exam 1 sit next to each other, and the number of ways of doing that is 6 factorial times 7p3. That's it for this lecture. I thank you for your attention once again, and in the next lecture we will look at the number of combinations of objects where we don't care about the ordering of the different objects in question. Thank you for your attention.